been all along, confessing twilight on and on, without a clue, without a sign, without grasping it. The real question to be asked: where have I been? I'm a sharpshooter at Post Masquerade, hiding both face and mind, all free for you to draw. I'm a sharpshooter, what else should I be? Please don't take off my mask, revealing dark. Moments of calm, nothing left to be found. A mirror right in front of me, that's where I found an empty glass, reflecting that's a truth. It's telling words not to be told. I need that mask. I'm a sharpshooter at Post Masquerade, hiding both face and mind, all free for you to draw. I'm a sharpshooter, chained down to my core. Please don't take off my mask, my place to hide. I can't tell you how to see me, just a cage of bones. There's nothing inside. Will it unleash me, burning down the walls? Is there a way for me to break? I'm a sharpshooter at Post Masquerade, hiding both face and mind, all free for you to draw. I'm a shapeshifter, have no face to show. Please don't take off my mask, my disguise.
Hi everybody, welcome to the last lecture of Chem 161. Let's see here. So, come hell or high water, we have to finish it. So, we're going to finish off the rest of Chapter 4, which is actually part Chapter 10. And then we'll do the very, very brief Chapter 5 explanation, which will have lots of pictures that nobody's going to care about, but I'm going to talk about anyway because it was important for me in grad school. We'll talk about that little story when we get to that. So, last call for Chapter 3 quiz. I know you have been putting off quantum mechanics for as long as possible. You could do that no longer. You must finish the quiz by tonight before it closes, or you will be unable to do so. All right, so that's the wrong window. Let's go back here. So yesterday we were talking about intermolecular forces and how they are the attractive entity that occurs between molecules. They are weaker than bonds, but they arise from Coulomb's law. So what we're going to do is we're going to look at situations where we can make Q be as large as possible, but still not be a whole number, because that would imply ionic. All right, so the first thing that we're going to look at is called the dispersion force. You may also hear this called the London force. They're the same thing, just two different names depending on which text you're looking at. What the London force is, or the dispersion force, is an uneven distribution of electron density around a molecule. So in frames 1 and 2 on the screen here, I have two situations where the electrons are more or less roughly opposite sides of the nucleus. So there is no one area around this atom that is more negative than the other. But in frame 3, both of my electrons just happen to be on the left side. So at this instant in time, I have a delta minus on the left side of this atom and a delta plus on the right. And if I had anything that was negatively charged, it would look at this and go, oh, look, there's the nucleus, and be attracted to it because it's the opposite charge. Because those electrons aren't in the way to repel it and shield it away. Now, the instant that the electrons return, and the probability of them being back on that side at any other instant is the same as it is at any instant, so like roughly 50%. That electron is going to be like, oh, never mind. Just kidding. So these forces are weak because they require electrons to randomly be distributed across a nucleus in an uneven fashion. But in the event that they are in an uneven distribution around the nucleus, they can create a temporary dipole. Now, a temporary dipole is not very strong, unless you have a lot of these temporary dipoles all turning on and off repeatedly. Then it's kind of like you have a weak dipole that is just always on. So, how do we create dispersion forces? Well, if a dispersion force is the uneven distribution of electrons, which that's our definition, that's our dispersion force right there. Then if I had more electrons, I'd be more likely to have them be unevenly distributed, right? So that's what's going to happen here. If I can make something have more electrons by substituting out atoms that have more electrons around them, I can get bigger dispersion forces. Furthermore, it doesn't matter what atoms I am using, because all matter has electrons. All matter exhibits dispersion forces. So when we go to ranking how molecules can hold themselves together through intermolecular forces, everything's going to have at least dispersion. Dispersion is the default choice. And again, the more electrons there are, the more likely this is to be able to occur. If I can make a molecule exhibit this polarization, where I have the electron shoved to one side rather than the other, then it will exhibit dispersion forces more often. So a molecule is polarizable if it's easier to induce dispersion forces in it. And the easiest way to do that is just look at a bigger atom. Bigger atoms have more electrons, and the corresponding feature that we can just link to that is molar mass, because that's a lot easier to count. The higher the molar mass for a molecule, the more electrons it will have, the more polarizable it is. So if you're arranging molecules by intermolecular forces and they all have just dispersion, the ones with the highest mass will have the strongest dispersion forces, because they are the ones that are most likely to have an uneven distribution of electrons. So we can see that in the noble gases here. Noble gases are nonpolar because they're just a single atom flying around. They don't make any bonds. They just exist on their own. And we can look at the number of electrons, which correlates to the molar mass. Not 1 for 1 or anything like that, but heavier things have more valence electrons around them. So you can see as we go from helium all the way down to xenon, the boiling point goes up very, 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 very fast. So helium has very, very few electrons. It only has 2. It's only allowed to hold molecules together in the liquid phase at temperatures below 4 Kelvin. That's pretty cold. That is negative 268 Celsius or so. Neon has 10 electrons. You can get enough of a dispersion to keep it as a liquid until 27 Kelvin. So, minus 250 Celsius. That's... Excuse me. But as we increase the number of electrons, the boiling point goes up and up and up and up and up. So xenon actually boils at 165. That's not as unreasonable. That's only negative 100 Celsius or so. There's nothing reasonable about negative 100 Celsius. Like, don't go out in that. Now, these are just the noble gases, but the trend is the same for molecules that are just like carbon and hydrogen. Anything with just H and C in it, a hydrocarbon, is nonpolar. And so if I take a really, really, really big molecule with lots of C's and H's in it, it will eventually become liquid or solid if I have it be a large enough chain. Many hydrocarbons are liquids at room temperature. And then eventually, as you make those carbon chains longer, they become solid. And it's because the dispersion forces become significant when you have huge, huge molecules and tons of electrons. There's always going to be an uneven distribution of electrons somewhere in your molecule, and that will be attracted to other molecules and hold them together. Now, what happens if you have two molecules that have the same atoms, but their structure is different? So, for example, N-pentane here is C5H12, and that is if I have my carbons chained in a row like this, with H's coming off. I'm not going to draw the H's, but the H's are each of these dashes. So that's N-pentane. Neopentane says, okay, I'm going to put my carbons around a central carbon, and then each of those carbons is going to have a hydrogen coming off of it too. So these are both C5H12. So they have the same number of electrons, but they have a different structure. And you could probably imagine that I could connect these carbons and hydrogens in any arrangement I want to, because, like, for example, if I broke this bond here, I could connect that carbon to any of these other H's, so I could put it here instead. And then the H that I replaced would go in that spot. So there's all sorts of isomers that I can use to construct these hydrocarbons. How the heck do I arrange those by boiling point? Or are they all going to be exactly the same? Well, it turns out that they aren't the same. And that's good news for us, because that allows us to separate them. And the reason they aren't the same is the following. If I write a line around the molecule for its surface area, and then I take a matching molecule and put it next to it, and then I try and draw where those two molecules can have interactions. So that would be all in here. These molecules are very close to each other in that region, and so they can exchange dispersion forces, like so. For this molecule, they can only contact each other where they touch, right? Which molecules are going to be more likely to stick together? Well, imagine if the molecules were just covered in Velcro. Which two molecules would stick together? Well, obviously it'd be this one, because there'd be more Velcro touching Velcro and hooking onto it, right? You'd have to pull the Velcro apart over a larger area. In this case, the area where they're contacting is small, so they won't stick as easily through dispersion. What that means is that the boiling point for the molecule on the left is going to be slightly higher because the dispersion forces are stronger. And you can see that here. The boiling point is 25 or so degrees higher. So this gives us a way to measure intermolecular forces. We're just going to look at boiling points. When something boils, it means that the molecules no longer have enough energy to stick, or they have too much kinetic energy, and they can no longer effectively stick to each other. The temperature at which that happens is going to be relative to the strength of the intermolecular forces, because a higher temperature means higher kinetic energy, and molecules that have higher kinetic energy are less likely to stick together, or will need stronger forces to hold them. So if a molecule gets to 10 degrees Celsius before it starts to boil, that means the forces holding it together were weaker than those for the molecule that boils at 36 Celsius, because you need that much more energy to get those N-pentane molecules torn apart. And the reason for that is because there's a greater surface area for it to stick to other molecules. All right, so what I want you to do is, for our dispersion discussion here, I want you to choose the compound that has the higher boiling point. Remember, a higher boiling point means stronger intermolecular forces. So choose between chlorine and iodine, or oxygen and nitrogen, or hexane and octane. And then from the bottom set of compounds, one of those is a liquid, one of those is a solid, and one is a gas at room temperature. Which is which, and tell me why. Type your answers in the chat. This should not take long. I'll give you 3 minutes to do it. All right, 1 more minute. We'll go over the answers. All right, very good. So, hopefully you came to those answers because you were just counting the number of electrons, and that's exactly what you're doing. So, whichever has more electrons will have the stronger intermolecular forces. if the molecules are completely nonpolar, which these are. So iodine has more electrons than chlorine. Oxygen has more electrons than nitrogen. And octane has more electrons than hexane. Something interesting that you can do is you can distill liquid oxygen right out of the air if you have liquid nitrogen. And I had no idea you could do this. So if you take liquid nitrogen and you take a tube and you put the dry tube in liquid nitrogen and just let the bottom sit there, any oxygen in the air will condense and then collect at the bottom of your tube, and you'll just have a tube with liquid oxygen in it. Now, you'll also condense out anything else in the air, so that would be like CO2 or argon or water. But there's far more oxygen in the air than there are of those other things, so the primary liquid component in there will be oxygen. Liquid oxygen, by the way, is blue for some reason, and I don't know why. Like, it's like a sky blue. It's actually not the reason why the sky is blue, but for whatever reason, it ends up being sky blue. It's also flammable as hell, so... Alright. And then down here, determine which is the solid. The solid's going to be the one that has the highest boiling point, because we'd have to heat it up even further to get to liquid and gas. That's clearly going to be this one. The gas is going to be the one with the lowest boiling point. In fact, its boiling point is already passed. It's at a temperature below room temperature. I don't know why I was going to write gas. This isn't D&D. I'm not cursing you to do a quest. And then finally, this must be the liquid, because it has intermolecular forces between the two extremes. It has a number of electrons between them. Alright, that's dispersion. Again, everything has dispersion. We're going to default to that. Now, the next three intermolecular forces we're going to talk about, we're going to look at specifically for small molecules. So, we're going to talk about what happens with large molecules later. But for small molecules, if I have a molecule that's small and is polar, it will have a dipole. If I have two things that have dipoles, so maybe this is my molecule, and I have a second molecule, it will be attracted to the opposite charge, just like any two pairs of charges would be. Now, these charges are permanent, which means that, unlike dispersion, they hang around and are always present, so they are stronger. If I have acetone here, acetone has the very polar CO bond, carbon has an electronegativity of 2.5, and oxygen is 3.5, so the delta En is 1.0, which makes this a polar covalent bond. And that dipole persists as long as the molecule is in this arrangement of atoms. That does sound like fun. I'm gonna have to YouTube that. Now, if I take multiple acetone molecules, they will line up in such a manner such that the dipoles will pair up with opposites. And in doing so, they stick together more strongly. So here I have two molecules. I have acetone and butane, which have about the same molar mass. They both weigh 58 grams per mole. And the boiling point of acetone is 50 Celsius higher. A Kelvin and a Celsius are the same thing, remember. So butane has a boiling point of -1 Celsius. And acetone is around 50 or so Celsius. So it stays a liquid at room temperature. And this is true of all things that have dipoles. They will all stick to each other more effectively. If we look at different molecules and measure their dipole moment, the dipole moment just being how polar are they, we can see that the boiling point goes up as polarity increases. Now, it's not a linear trend. As things become more polar, they just have higher boiling points. These molecules were chosen because they all have roughly the same molar masses. They're all about 40-ish. But the stronger the dipole, the stronger the intermolecular force, and the higher the boiling point is. How do you determine how strong the dipole moment is? We can measure it experimentally. The unit of dipole is called the debye. I used to call it Debbie. And then I learned it was the debye, and I was very upset that it was not the Debbie. Just because I like saying 2.69 Debbies, or 4.41 Debbies, or whatever. Now you can measure that, or what you can just do is look at delta electronegativity. That's what we're going to do, because measuring debyes is not trivial to do. Now, if you have molecules that are polar, and you try and mix in molecules that are nonpolar, what ends up happening is the following. Here's a molecule that's polar. So here's my water molecule, for example. And I'm going to give it a choice. Should it interact with something that is nonpolar or something that is polar? Which of these will it prefer? And note that when I don't put dipoles in here, temporary dipoles do exist, but the second that I start drawing it, it will have disappeared, right? So it might as well not exist. And the answer is water is always going to choose the option that gives it the strongest interaction. So water hangs out with itself. It will form a dipole interaction. I almost said hydrogen bond, which is actually the next step that we're going to talk about. It will form a dipole interaction with itself because that is a stronger interaction than with a nonpolar molecule like pentane. Pentane only has dispersion forces. So these two molecules separate out. So this is only dispersion. Water also has dispersion. And it has dipole. This is weaker. This is stronger. So this is the one that is predominant. This over here is all this molecule has. So we call this like dissolves like. Whenever you compare two liquids together, if you have polar liquid and nonpolar liquid and you try and mix them together, they don't mix. So this is oil and water. It's exactly what it is. Oil is nonpolar, water is polar. They don't mix together. They form two separate layers. So if you have Italian seasoning, or not seasoning, Italian salad dressing, the oil will just sit on the top and it won't mix with the aqueous part on the bottom. Even when you shake it, you can shake it all you want, but they will separate out because of intermolecular forces. Now, if you shake it enough, that gets you a mixed enough that you can pour it, and then you get both the oil part and the water part for your salad. So that's good enough for our purposes, but when you leave it there, it will separate out. So again, the thing to remember is like dissolves like for trying to determine if something will form two layers or not. If two things are polar, they'll mix. If two things are nonpolar, they'll mix too. But polar and nonpolar will not mix. And it's because of intermolecular forces. They would rather, the polar thing would rather stick to other polar things. Oops. All right, so what I want you to do is, looking at these molecules, I want you to predict the compound that has the higher boiling point. And so you'll need to predict this based off of which molecule is polar versus nonpolar, or which molecule is more polar than the other. To figure out if it's more polar, you'll need the electronegativity chart. You can find that in Unit 4 at the start. So I'll give you a minute or two to make your predictions, and then we'll go over the answers. One more minute, and we'll go over the answers. All right, so let's choose the compound that has the higher boiling point. Between water and gasoline, which one has a dipole moment? Well, gasoline's all C's and H's, and we said that that's nonpolar. H2O, on the other hand, is very polar, so it should have the higher boiling point. Now, you would know that it has the higher boiling point because you have to heat water up to make it evaporate at any appreciable speed. But if you spill gasoline on the ground, it evaporates almost instantly, right? So its boiling point must not be that much higher than room temperature. For CH3Cl, if I draw the Lewis structure of CH3Cl, and we did this yesterday, we found that it has a dipole that points in this direction. It's not much of a dipole, but it is a dipole. CH4, on the other hand, would just have dispersion. So that means that CH3Cl should have the higher boiling point, and it does. Next we got HCl and HF. And these are both polar in the direction away from hydrogen. But chlorine has a lower electronegativity than fluorine does. So the delta En will be smaller for HCl and larger for HF. Since that's a larger dipole, it's a stronger attraction. So HF should have the higher boiling point. We'd have to apply the same logic for ammonia and water. What gives you the stronger electronegativity difference? NH or ONH? And it is ONH. So water is a much higher boiling point than ammonia does. Water and ammonia actually do something special, but water does it particularly well. And that something special is actually on the next slide. We're going to talk about a special dipole interaction called hydrogen bonding. Now, it's called hydrogen bonding, but it's an intermolecular force and it's not a bond. So the reason we call it hydrogen bonding is because hydrogen sort of sits between the two important atoms that we are connecting through intermolecular forces. The way that you make a hydrogen bond is that you need two things. Hydrogen, duh, it's a hydrogen bond, right? And then very electronegative atoms. There are only three candidates: nitrogen, oxygen, fluorine. They have to be very electronegative and they have to be very small. This is why chlorine gets disqualified. Chlorine's too big. Now, what ends up happening is that water, as shown here, has a delta plus on this side of the bond and a delta minus on that side of the bond. I could write the same interaction like that on the second molecule. So if I align my molecule in this way, I can get an alternating minus plus minus, which is a strong attraction between these two molecules. Remember, that's how covalent bonds work, is you have the electrons sitting between the nuclei of two atoms, so you get a plus minus plus attraction, right? The same thing should happen here. Now, because hydrogen is so small, it can get real close to oxygen. It doesn't have a pesky electron cloud to repel away the other electrons. I mean, hydrogen has an electron cloud, it's just not very big. It's only one electron. And that electron is going to be sitting over between the atom it's bonded to. So because hydrogen is tiny, it can get right up next to very electronegative atoms. And if you remember Coulomb's law, E is proportional to Q1, Q2 over R. If I make this small, this goes up. And if I pick things that are particularly polar, this goes up some more. So if you can get hydrogen to be bonded to one of these three atoms and then pointed at the electron pair on another copy of those atoms, you make a hydrogen bond. So all the hydrogen bonds are shown on this slide here. I'll just fill this in here. And they have hydrogen that is between one of these three elements, NO or F. One of those sides has to have the bond. The other one has to have the electron pair. When you are the molecule that is providing the bonded H to engage in the hydrogen bonding interaction, we call this the hydrogen bond donor, because it's donating this. The atom with the free electron pair on it is the hydrogen bond acceptor. Not all molecules are hydrogen bond donors. For example, acetone cannot hydrogen bond to itself because there are no F's, O's, or N's down here. But if there is an O up here, and if I had water come up next to it, I can make a hydrogen bond that way. Now, that's important for mixing. Things will be soluble in other things if they have strong intermolecular forces. They will mix together. We're not going to worry about solubility so much in this class. Oops, I didn't mean to hit that one. I meant to hit this one. We're just going to worry about boiling point and whether molecules will interact or not. The molecule on the left can hydrogen bond because I have an O bonded to an H. The molecule on the right cannot. It is only polar. So I can point this H at the O on another ethanol molecule, like this. I can make a hydrogen bonding interaction. And the molecules will stick together more strongly than if they were unable to do that, as in the case of dimethyl ether. And so when I look at the boiling points, the boiling point of ethanol should be higher. And oh, is it higher? It's higher by over 100 Celsius. They have exactly the same formula, C2H6O, but ethanol boils at 78 Celsius, and dimethyl ether boils at negative 22. Thanks to hydrogen bonding, ethanol stays a liquid at room temperature, and we can drink it. Yay! Don't drink dimethyl ether. Just don't. Here's a chart that shows boiling points. Now, the only substance that has hydrogen bonding capability is water in here. The rest of these are pretty much dispersion. So this bottom set down here, these are all dispersion. And what you see is there's this kind of trend for dispersion. The intermolecular forces holding these molecules together are completely dispersion. And the boiling point goes up as the mass goes up in a pretty linear fashion. Now, up here for H2S, H2SE, etc., the same thing more or less happens. You get a linear trend until you get to water. Water is 200 Celsius higher than you would expect it to be based on its mass and ability to do dispersion forces. Instead of boiling at positive 100, it would boil around negative 100 if hydrogen bonding wasn't a thing. That'd be a really cold shower in the morning. It would wake you up real fast. But more importantly, hydrogen bonding and the interaction forming and actually being able to form gives water its stability to the point where we can use it in things like life. Water is a great fluid medium for molecules to exist in and move about and undergo chemistry, which is how all of this started in the first place. All of this being life. All right. Let's look at some example molecules. So here's formaldehyde, fluoromethane, and peroxide. Only one of these is a liquid at room temperature because it's the only one capable of performing the intermolecular attractions between two molecules of its type to hold them together to be liquid at room temperature. Which is the liquid? Well, let's look at the intermolecular forces that are present. So here I have delta plus and delta minus. But I cannot hydrogen bond, so this is just dipole. Here I have a pretty good dipole going in this direction. And then here I have hydrogen bonding. I can point the OH at the O on another peroxide molecule to make my hydrogen bond. So those will stick very effectively. So only hydrogen peroxide will be a liquid at room temperature. And the reason for that is because it's the only one that can hydrogen bond. The rest are dipole and do not stick to each other effectively enough to be liquids at room temperature. All right, for these pairs, what I want you to do is tell me which one has the higher boiling point. This time I have combined all the intermolecular forces together. So this is sort of your IMF grab bag. Which one do you predict the answer to be? One of these is a trick question, and the other one is actually very difficult to answer. So you could call it a trick question also. So there's two tricky ones. One is tricky because, haha, gotcha. The answer is really easy. But the other one is tricky because it's really hard to predict the answer. But the other two, you should be able to figure out really quickly. So I'll give you 2 or 3 minutes to figure that out. We'll go over the answers in just a bit. One more minute. We'll go over the answers. All right, so in the first case here for hydrogen fluoride and hydrogen chloride here, I lost my cursor. There it is. HF can form a hydrogen bond, but HCl can't. So hydrogen fluoride is the winner. H2O and H2S, water can form a hydrogen bond, but H2S can't. So water will have the higher boiling point. Now, between H2S and H2SE, you could just go back to the previous little chart that we had here and go, oh, of course it's higher. But if you don't have that chart handy, then you might look at H2S and say, okay, well, H2S is more polar, but H2SE has more dispersion because it's way heavier. Which one do you pick as the answer? And the answer is, at this point, it's difficult to determine. Because this is where we sort of get into the gray area. This is effectively what I would call a small molecule, but I would not call this one a small molecule. I call this a medium. And so it gets very difficult to compare these two. So in that case, we have to do the experiment and look up the answer. So on a test or assessment, I would not give you this specific question. But the reason I put it in here is to bring up the discussion of this is not all clear-cut black and white. There is not always a best answer, because at some point, the dispersion forces are going to become so strong that dispersion is the most powerful force there is, but only if there's tons of it. Dispersion is the one that you can keep on multiplying. All the rest of these only work when it's small. And then for the last one, we can hydrogen bond and then whatever this is, right? So, of course, the answer is this one. What? But this can hydrogen bond. Why would its boiling point be lower than... Oh. It's an ionic compound. Remember, ionic compounds have actual charges involved. And actual charges stick together far better than partial charges. In fact, if you look up the boiling point of ammonia... I had this here. So boiling point of ammonia. Ammonia boils at... I just want you to tell me the boiling point. I don't want to know all these things about that. There we go. Negative 28 Fahrenheit. So minus 28 F. I don't have Celsius, unfortunately, there. But the boiling point of NH4Cl is 968 Fahrenheit. So, things that have actual charges in them will have really, really, really high boiling points. Okay? So, don't fall for that one. That is something I expect you to know. Ionic compounds have stronger interactions because they're actual bonds, as opposed to intermolecular forces. So, something with actual ionic bonds will have a much higher boiling point. And by much, I mean like 1,000 degrees higher. All right, any questions, let me know. We're going to do the last intermolecular force, and that's the ion-dipole force. Now, ion-dipole forces are not really an intermolecular force because they are just the force in which ions dissolve into water through. So, these don't hold things together and thus won't explain any boiling points or anything like that. But what they will explain is solubility. This is why ions dissolve into aqueous solution so effectively through these forces, ion-dipole. Now, if we're looking at Coulomb's law, and we said that, okay, partial charges can hold together effectively, if I make one of them just a whole charge, they will stick together even more effectively. So the attraction between a fully charged ion and the partial charge of water molecules around it is particularly effective. And that allows water to dissolve various ionic compounds into it. Now, as far as a strength, the strength of this ion-dipole force is the strongest of all the four intermolecular forces, but it has no influence on boiling point, because you can't boil Cl-. It's not a pure pure substance. It's a mixture. So let's summarize our intermolecular forces here. Dispersion is the uneven distribution of electrons, and it is the weakest unless the molecules are huge. The next most important, not important, the next most powerful interaction is the dipole force, and that forms between the dipoles of polar molecules. And then the strongest intermolecular force for pure substances is the hydrogen bond. And you need to have special components for that. And then finally, the ion-dipole force just occurs between ions and dipoles, and is the strongest, but again, this is not for boiling point, because you won't ever have ion-dipole forces in a pure substance. The rest are for boiling point. So, weak, strong. Now, on quizzes or exams, I may distinguish between a small molecule and a large molecule. This gradient as shown is for a small molecule. Okay? So for a small molecule, dispersion is the weakest force, hydrogen bonding is the strongest force. For a large molecule, dispersion is the strongest force. All right. Now, before we take our break, I want to show you one last little thing about dispersion forces and how they hold things together. So here's going to be some videos of liquids interacting with themselves. So the first is water. When water exhibits intermolecular forces, that means that the molecules don't want to spread out. They want to try and contract as much as they can and stick together. This causes them to coalesce into a sphere. So if you spill water on the counter, it tends to bead. You'll see the little beads of water on the surface. This phenomenon is called surface tension, and the best place to demonstrate this is space. So let's go to space. Space, I love space. And we're going to look at water, which is right here. Here's my water. And what they're going to do to this water is they're going to use air to try and distort its shape. So here's my water. I'll just mute this because I don't want to hear them talking in the background. Oh, there goes part of the water. It's escaping. And you can see that it really tries to maintain its shape. Even when you distress it, here's some air. Boop. Now, this is outer space, so there's no gravity pulling it in any direction. And so that force moves through the water blob, I guess we'll call it. That metal thing that you see in the middle is a hoop, and the water sticks to the hoop so that it has something to stay on and doesn't just go flying off. Oh, that little bit's getting away there. We'll just scoop that up. Now, so you can see it's very difficult to break the surface tension of water because water wants to stick to itself a lot. And in some of these, you could see like the little bit of water tries to rejoin the rest of the water. But it's very difficult for that to happen because once the water is left, see, there goes that droplet. Whoops. If that water droplet was reintroduced, you would have to break the surface tension on both sides of the water, the big glob and then the droplet. So that's cool and all. Now, what other effects does surface tension have? Well, you could bounce stuff on it. So I guess this is useful for like fly fishing. I don't know. But you can bounce really tiny things on the surface of water because the intermolecular forces will hold the water together. And the other object that you're placing on it has to pass through that. Now, people are obviously too heavy, and their force is distributed on too tiny a space for intermolecular forces to hold them up. But if you can make your surface area large enough, you too can float on water. Or stand on water, or whatever. But you'd have to have a very high surface area. Now, the last effect about intermolecular forces that I like talking about is viscosity. So viscosity is how resistant liquids are to flowing. Liquids that have strong intermolecular forces tend to be very viscous. Now, water's kind of a weird exception. It has very high intermolecular forces, but it's very, very small. So all the molecules stick to each other, but then they still flow out of the bottle. In order to make molecules not flow, we can tangle them on top of each other. So if I have molecules that have a bunch of single bonds, and those single bonds can be drawn in such a way that I can make like a loop or a figure 8 or something like that, that I can twist the molecule up and get it stuck in other molecules, those molecules will be viscous. Viscosity depends on temperature and intermolecular forces. The stronger the intermolecular forces are, the more likely the molecule is to stick to itself, and the higher its boiling point will be. And also, the higher its viscosity will be. And that brings us to this molecule called pitch, which might be the most viscous substance that I am aware of. And so its structure looks like this. Each of the intersections on this structure is a carbon. And at the end, we have carbons that come out in tetrahedrons to other carbons. These are all just little hooks waiting to hook on each other. So this is what pitch is. It's a bunch of carbons attached in a bunch of rings, and there's tons of them in here, so it has a very high dispersion force. And then the molecules have little, like, grabby ends, because they're all tetrahedral claw-like structures. And those can latch onto other molecules that are passing by. So the viscosity ends up being super, super high, as well as their intermolecular forces. Now, if you took this stuff and you hit it with a hammer, you would find that it shatters apart like any other solid. In fact, it looks like a solid. But then somebody decided, you know what, we're going to do an experiment. I want to see if this is actually a liquid, because it's molecular. And so this is what they did. They put it in a funnel and let it pour out, and they decided to just let this go in a bell jar for as long as it would take for a drop to pass through, just as a test to see how strong these intermolecular forces were. And they found out this stuff is actually a liquid. And it's called the pitch drop experiment. The pitch drop experiment is probably the world's longest experiment. They started this experiment in 1927. It is still going. Here's how the pitch experiment works. They put some pitch into a funnel. They put the funnel in a bell jar, and they put a beaker under it. It took 3 years before the substance just settled into the funnel. At that point, they were allowed to start the experiment. Then they cut the bottom of the funnel off. The pitch was allowed to flow through into the beaker beneath it. The first drop fell through 8 years later, in 1938. Now, this experiment, which has been run at a university in, I believe, Australia. I think it's Queensland. I'm not sure. I can look it up, because I'm going to show you the video here in a second here. For the longest time, people never had seen the drop. They'd come back the next day and then be like, oh, we missed it. It's a once in like a 10-year event. And then, so like, this experiment has been going on for 80 years, and the pitch has dropped 8 times, and nobody had ever seen it until, and this happened after I started teaching this topic because someone told me about it, and I just thought it was so cool. They told me about this, and somebody got the idea, hey, why don't we put a webcam on it? Because around 2009, that was when webcams started to become a big thing. Everybody had a webcam. Okay, we'll point one at our pitch drop experiment. And so they did that, and this is the video they recorded. Now, I'm going to capture this on the screen here, but what you'll want to look at is actually in the bottom left corner. I haven't actually captured that part yet. I'm going to make this real big here. So you can kind of see right there, it says Trinity College in Dublin, which is not in Australia at all. Maybe this is in Ireland. Who knows? When I hit play, the cover is going to go away, and you can see how fast time is going. You can also tell by this clock in the background here. Okay, so here we go. It's Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And this was in 2013 when this happened. And look at the pitch drop. There it goes. There it goes. Oh, there it goes. Hooray. And for some reason, there's a video about sushi. Or 72-hour beef Wellington. I watch videos about food, so. So, that's how many days that took. And it, at long last, it breaks apart. So, these intermolecular forces in pitch are so powerful that it just takes so long for those molecules to separate apart. Now, if you want to read more about the pitch drop experiment, I'm actually going to post this link into the chat because there's a chart on there that shows how long it took for the pitch drop experiment to occur in each case. And I just want to talk about this really briefly. I'm going to hide the answer because there's a footnote there that you can see for the drops that are bigger. Why would the pitch drop experiment take almost 1.5 times as much time for the last 2 drops? And a lot of people immediately think, oh, well, because there's less of it, so it flows out more slowly because the last few drops take longer, right? Well, no, there's plenty of pitch in there. Why would the drops take 30 extra months to drop through? Or, in other words, an additional 3 years for the next few drops to pass through. Oops, sorry, I was reading about the... This was Queensland. This is the Queensland experiment. Apparently, the Trinity College at Dublin that we watched, theirs started in 1944. But this specific one was the University of Queensland and was started in 1927. I'll give you a hint. Why might the last few drops take longer? You really have to think outside of the box for this one, but the answer is... it is colder. Why would it be colder? So in order for it to flow more slowly, it would have to be colder. What could you do to make it colder? What do you think a likely thing to do in the late 80s would have been? Yep, install air conditioning. So after the 7th drop, around 1988 or so, the university decided, you know what, we're going to install air conditioning because we live in fucking Australia. It's like 174 degrees in the summer. And so after that, the temperature was kept at a much more constant, lower temperature. And so it flowed a lot more slowly. So you could see that, like, this would be a very weird random error. Like, why is it suddenly longer? And the answer is, oh, we changed the experimental conditions. So that can happen. All right, that's the end of chapter 4. Believe it or not. I don't care about capillary action. You can read that if you want later. All right, so there's our summary at the end. You can read through all these on your own time. I am going to put the title card back up here. My timer didn't show up because I had to maximize it here. So I'm going to put the music back on. And we're going to have the very last break time of Chem 161. So I'll see you in a little bit. Whoops, I was looking at my phone. Alright, let's talk about the last little bit. So, some things to note here on the screen. So, first and foremost, we're not doing MO theory. So, this gets scribbled out, and this is actually half of the slides in this chapter. So, if you open the slideshow and you're like, oh, holy crap, or the PDF, I mean, you're like, wow, there's a lot of slides. How are we going to do all this tonight? We're not. There's really only two things I want to talk about, and so one is in valence bond theory, and the other is in hybridized atomic orbitals. So I have something that I wrote out during the break on the Photoshop that I'm going to show you when we get there. But let's talk about valence bond theory real quick. Valence bond theory is a model, and the model is bad, but the model does provide a template for us to apply hybridized orbital theory to. Okay? Here is what valence orbital theory tells us. It says, okay, if covalent bonds occur when electrons are shared, and electrons live in orbitals, how do I make bonds form? Oh, I must share the electrons between atoms by overlapping the orbitals. And so what it says is, okay, I'm going to take my orbitals, I'm going to try and superimpose them on top of each other so they physically intersect. And so I have a bunch of different orientations of orbitals. I have all my S's on the left here. And I'm going to line up S with S with P in each of the directions. We're going to see which ones overlap. So this first orientation, the sphere goes in all directions around the axis. So if I just slide this right up next to this front part and this side part here, those will intersect. So this will be an overlap. That was a lot louder than I expected, sorry. Now, if I do the same thing here, you'll notice that there's a gap here. The gap is on the XZ plane. And this orbital is going to fall into that gap. And so when I put them together, they don't overlap. This guy is just sort of in the front and this guy's in the back. Same thing here. This doesn't work. But because this orbital is arranged along the axis that I'm moving this orbital on, it will overlap. So valence bond theory says, okay, if I want to make bonds occur, I just need to overlap my orbitals. So I can overlap this pair up here and this pair down here, and then just arrange my s orbitals around axes however I want to get the other bonds, right? All right. In all of these models, the black dot in the center is going to be the nucleus. I'm going to make that a little bit easier to see here. Well, I would make it easier to see if I didn't mess up so badly drawing the nucleus. There we go. Oh, that's a better pen to use for that. There we go. Okay. The highlighted space between the two nuclei where my orbitals interact, so this right here, and this right here, that space is where my electrons, specifically the bonding electrons, reside. Now, interestingly, if I took two p orbitals and I lined them up parallel to each other, so not end to end, but parallel, I actually get orbital overlap. And I get this sort of strange arrangement where I have a plus for my nucleus, and then my electrons are up here and down here. But it still works. It's stable enough. So these arrangements lead to overlap where electrons can live in the overlapping regions. We're going to define these in two ways. I'm going to draw a big line through all the nuclei. And you'll notice that in these cases over here, the region where my electrons will be bonded is right on that line. But in this case over here, it's not. So we're going to differentiate these two different types of bonds. So the first case is what we're going to call the sigma bond. The sigma bond occurs if the orbitals overlap along what's called the internuclear axis. The other way to describe this is that when our orbitals are overlapping end to end, we're pointing them at each other. Now, with the s orbital, you don't really have a direction to point it in, but the p orbitals, you do. So if I point my p orbitals end to end, they overlap, and my bond will form in that region between them. That's where the electrons will reside. Now, if my electron density for the bond is between the two nuclei, like along the line that connects them, that's the internuclear axis, it's called a sigma bond. Now, if the electron density goes around the internuclear axis, so it's above and below, or in front and in back, because I could do the other p orbital where it's coming out of the screen and then going into the screen, we're going to call that a pi bond. So pi bonds arise from side-by-side overlap. And you can only do this with p orbitals. An s orbital cannot overlap the p orbital effectively. So these are the two types of bonds that can occur, sigma and pi. Sigma bonds are directly between the two nuclei, and pi bonds are sort of parallel around it. Now, why is this important? Well, it turns out that if you're making a bond between two atoms, there's only so many places you can put electrons. So if I did something like this, where I have 4 electrons going between my nuclei, I'm going to have one of these bonds goes directly between, and then the other one goes around the nucleus like this. So I'd have 2 electrons here, and then the other 2 go in the other set. So in other words, the first bond between any 2 atoms is always a sigma bond. And if I form a second or third bond, those are pi bonds. We're going to show illustrations of that later on in the chapter. All right. Now, valence bond theory tries to take our orbitals. There's our discussion, though, we just said. The first bond is always a sigma bond. The further bonds are pi bonds. So your double and your triple bond are pi bonds that are formed from there. So if I asked you to describe this bond, you would say it's a sigma bond. If I asked you to describe this is a sigma and a pi bond. And this would be a sigma plus a pi and another pi bond. And the reason for this is entirely geometry. Once you put electrons in the middle, you can't put extra electrons there. They would repel. So we have to use the around space, the above and the below that bond. Our electrons can be in that orbital overlap. Oh, I love it when I preempt my slides. I feel so dumb. Like, I could have hit the space bar and just shown you this, but that's okay. Now, a lot of people kind of think, like, oh, it's the last day of class. What we're probably learning on the last day, I'm probably going to forget. I'm going to give you permission to forget about this until you get to OChem. In organic chemistry, you're going to talk about sigma and pi bonds all the time. And that's kind of why I do Chapter 5 last on the last day, is because this is cool and all, but you're never going to use this until OChem. And almost all of you aren't going to take OChem unless you're a biology major, in which, haha, you get to take OChem. If you're an engineer, you get to stop at 162 or 163. Lucky you. Or unlucky you, actually, if I'm going to be realistic. I thought OChem was super awesome. All right, so what I want you to do is I want you to, in this molecule as drawn, count the number of sigma bonds and count the number of pi bonds. But you only have 60 seconds to do it, okay? So, good luck. I'll be right back, and then we'll go over the answer. Type in your answer in the chat when you got it, by the way. You didn't even need the whole 60 seconds, but finish counting, and we'll see if you get what I got to. So, here's how I do this. This can get really, not difficult, but obnoxious, I guess we'll say, because it's hard to keep track of what you've done. So I draw lines through my bonds. I go 1, 2, 3, 4, 5, 6, 7. So that must be sigma. And then I will draw lines through anything as a double. So 1, 2. There you go. So there are 7 sigma bonds and 2 pi bonds in this molecule. If you had a triple bond, you would have to do something like this through it to indicate that you're counting your pi bonds, 2 of them there. All right. Do I want to talk about this? Not. I don't. We've already talked about overlap in chapter 4, so this is fine. We don't need to talk about that again. Valence bond theory is unfortunately bad, but the premise is pretty sound. So we're going to talk about the premise here. The premise is, and we showed this when we were doing Lewis structures, if I want to make a covalent bond, I use orbitals that have unpaired electrons in them. That's pretty easy, right? We've been drawing our Lewis dot structures all along with things like this, where I would take this electron and we'll pair them together, right? Now, one of the problems is that our Lewis structure doesn't really match with what our electron configuration diagram would be for carbon. So if this was 2s and 2p, this is what carbon looks like. Whereas the actual diagram that we would need to resemble the structure that we see over here, I'd have to do something like this to it. And yet, by all things we observe, this is correct. Carbon has 4 spaces it can bond to. We can treat it as if it has 4 unpaired electrons, but very clearly it doesn't. This is its electron configuration because we did PES on it, right? So what the heck is happening here? If I look at a molecule that this works for, like H2S, here's how this works. I'm going to pair H with one of the unpaired electrons on S, and I'll do the same thing over here. And so I'll make H2S. And then these electrons right here are just these guys right here. So now we can line up all of our electron diagrams with the Lewis structures that we are drawing. And the issue that we get to here is that this only kind of sort of works. Here's where it falls apart. What's the bond angle right here? Well, we know it's a tetrahedron, so it should be about 109.5, but these electron pairs push it down, so it's a little bit less. But if I were to draw all of my orbitals on a coordinate axis, here would be the p's. Here would be my p orbitals. One going forward or up and down, left and right, and then forward and back. That was real bad. Let me try that again. I said one going forward and back. That's better. And then you have the s orbital over all of that. So we'll do the s orbital in a different color. What would the bond angle be between any of these axes, though? Well, it's 90, right? All of these the p orbitals are aligned in 90-degree angles. But clearly, we get a different angle for our geometry, because why the hell would we have been teaching you 109.5 for tetrahedral all this time? Like, that's a weird number to settle on in a weird structure. And the answer to that question is that, of course, this is wrong, because I forgot that sound effect was there. This doesn't capture the tetrahedral nature of geometry. So valence bond theory sort of fails, but it provides a good starting point. And that starting point is, well, if I can go back to this, or let me just draw it again, actually. if I can somehow do this and have 4 orbitals that are all unpaired, I could have 1 electron in each of those, and then all of those electrons would naturally repel in an orientation that would create a tetrahedron. So here's the center of my atom here. And my 4 unpaired electrons would go to the corners here. So what do I do? And the answer is, well, obviously our model must be wrong. Valence bonding theory is got something wrong with it. And that something that is missing is called hybridization. And so that's what we're going to look at in this section, which is the last section. And I have like 15 or 20 minutes to talk about it, so plenty of time. You know, plenty of time to sneeze, right? Okay. Hybridization, I'm going to talk about the answer before I talk about the theory. Here's the answer. Oops, there would be the answer if I didn't cover it with PowerPoint. Boop, there you go. All right. We're going to assign a code, a hybridization code, to each geometry. Okay? These are the codes. I'm going to ask you on the quiz or the exam, what is the electron geometry of this molecule? And all you gotta do is figure out how many electron groups are around it and then give it the proper term: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, or octahedral. Then I might ask you, what is the hybridization of that atom? And you're going to give me this code based on whatever geometry you picked. If this is all you have time to study for Unit 5, stop the video. That's all you need to know. Just write this down, bring it to your test, and that's good enough. But for the last 10 minutes or so, what we're going to do is try and explain where these letter codes come from and how bonding works. All right, here's our carbon energy diagram on the slide here. I had to click on the thing. I need to unpair those electrons somehow so that I can get 4 valence electrons available for bonding. So here's what we're going to do. What we're going to do is we're going to mathematically add and average all of these orbitals together. So what that means is that I'm going to take the overall energy of all of these, add them together, and divide by 4. And this process is called hybridization. And when I do that, I will get out 4 orbitals that will have an intermediate energy. Of course, it's the average. And then I have 4 electrons to put in there, which I will then fill using Hund's rule. Now, this is a conceptual experiment. Why would orbitals hybridize together when obviously these are in higher energy positions than before? These two are in much lower energy, right? So why would this happen? Well, if I invest this much energy to put some electrons up to higher energy levels, then when I make the bonds, I get that energy refunded back. And I actually gain energy from this process. I being the person who is moving the electrons around. The atom would then lose that energy back. It would have a lower energy state. So this is actually energetically favorable for this to happen in terms of where the electrons are, but only after bonding has occurred. So this diagram on the left is appropriate for elemental carbon all by itself. It's just carbon on its own. This diagram over here will be used for any carbon that we find in a bonded structure. And so we'll put the structure on the screen here. Now, the orbitals that we made, we gave a code. How did we get this code? Well, I put in an s orbital, and I put in p orbital, p orbital, p orbital, or 3 p orbitals. So I just write the code for what I put in. I put in an s and 3 p orbitals, sp3. Now, that would imply that I could hybridize fewer orbitals and get sp2, or sp. And yeah, you totally can. We're going to show that in a second. All right. Now, when you hybridize your orbitals, the number of orbitals you hybridize will be the number of hybrid orbitals you have available. So if I only wanted to hybridize 3 orbitals, I would get sp2. I'd pick an s and 2 p's. If I wanted to hybridize 5 orbitals, I could go s, all 3 p's, and then the d orbital, but only for elements in period 3, because those are the only elements that have d orbitals. This is why elements in period 3 can break the octet rule. They have access to d orbitals, which get hybridized. And again, only molecules have hybridized orbitals. So only molecules that have bonded elements will have hybridized orbitals. Atoms that are by themselves have their original electronic structure that we talked about in Unit 3. You only need to hybridize orbitals to make sure that you can form bonds. And when you form bonds, you will get the correct geometry that way. Now, since we're averaging their energies, we also average their wave functions. So all of these are shapes that are generated by an equation. Well, if you sum all those equations together and then average them, you get new results. And those results look like this. They look kind of like bowling pins. And there are 4 of them. And we can orient them in the 4 directions of a tetrahedron. And that's the shape that we expect for anything that is a tetrahedral geometry. So now our model that we've made fits with the expected shape that we observe. And if this is all over your head, it's okay to just summarize it as, okay, I'm adding shapes and averaging shapes to make new shapes. And those shapes overlap in the geometry that we expect. And that's totally fine. Now when we draw CH4, if I were to draw the Lewis structure, it would look like this. Here's the one that comes out, here's the one that goes back, and this one's in the plane. The electrons in CH4 go in the overlapping regions. That's a bad color. Right here, 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 and here. Now, if this were an in-person class and we had more time, I would actually make you draw these balloon structures. Obviously, I can't make you draw a balloon structure and upload it to Canvas. I mean, I could, but I'm not going to. So, that's more or less what you need to know about hybridization, is in order to make the models match what we observe with geometry, we hybridize them. And the orbitals that are used here would be, this is sp3, and this is just 1s. Hydrogen never hybridizes because it only has its s orbital to hang out. So hydrogen will always be bonding with just its spherical 1s orbital. Now, because these bonds go through all the internuclear axes, there are 4 sigma bonds in CH4. Let's look at what a p orbital looks like. Well, here's ammonia, first of all. Here's what nitrogen would look like. Nitrogen should have, after we hybridize, an electron pair and then 3 individual electrons. And then when I make its balloon structure, 3 of the... I guess I'll just draw it real quick. So here's nitrogen. I'm going to draw a sp orbital or sp3 orbital going that way, going this way, going this way, and going up. And then what I'm going to do is I'm going to put the electrons for... So I got hydrogen, hydrogen, hydrogen. Hydrogen has 1 electron. that it brings along. And then we'll do nitrogen's electrons in purple, we'll say. So nitrogen should have an unpaired or a paired electron that goes here. And then 3 individual single electrons. So 1, 2, 3 individual single electrons. And so that model matches with what we would expect. So hopefully with that example, you can see how we could start to generate any diagram we wanted to for any molecule by hybridizing its orbitals. Because then whatever the result is over here, that's what we're going to see around that atom. All right. How the heck do you make a double bond? Well, we said earlier that double bonds form in the overlapping region that is parallel to the plane. But the only way to do that is to use unhybridized p orbitals. So what we do is instead of hybridizing all the orbitals, we just hybridize some of the orbitals. Whatever is left over will be leftover p orbitals, and those p orbitals are reserved for the use of double bonds. So what does that look like in the hybridization diagram? That looks like this. I'm going to take my carbon in C2H4. I want to save this for a double bond, so it's not going to get hybridized. The remaining orbitals will be hybridized. And since I hybridized an S and then 2 P's, I get sp2 as my result. The remaining p orbital just hangs out there, and we use it to make a double bond. And so what does that look like? Well, if I have 3 orbitals, this will be trigonal planar. And I'm going to try and draw that really quickly. So if this is the plane of my paper, my orbitals would look like this along the plane in a trigonal fashion. And then my p orbital would look like this. It comes above out of the plane and then goes under the plane like that. So now that you've seen my shitty drawing, when I show you the real thing, it'll make a little more sense. Now, you might be wondering, well, wait a second, where is this overlapping with this? Like, what the hell is going on here? What has happened here is these atoms have been drawn really far apart so that you can see everything effectively. But if I were to draw this better, or if the diagram were to draw this better, this p orbital would actually be kind of more like this, so that they would overlap. But that looks really, really confusing when you have tons of stuff on the screen. So let's look at our sigma bonds here. So we have got this carbon-hydrogen bond, this carbon-hydrogen bond, and this carbon-carbon bond. So if I go like this, these 3 electrons would correspond to these 3 electrons here. And then I need another color that's going to show up here. We'll do green, I guess. This orbital or electron right here is this one right here. Notice that there's nothing down here. This entire, both the top and the bottom, that's all one orbital. So I just pair the electrons on either the top or the bottom. It's all the same orbital. So don't pair them in both places. That'd be adding extra electrons. And then everything I did for my carbon on the left, I do for the carbon on the right. So this second electron would be due to this carbon's sp2 hybridized electrons and the unpaired p electron that goes into that pi bond. So this right here, this bond is the pi bond, And the red bonds are my sigma. And that correlates over here. So here's my sigma bonds that I highlighted. And then my pi bond would be the green second line that I draw there. That's all just for the left carbon. Now you can do that with a triple bond. If you want to make a triple bond, I'm going to skip this example. We'll skip this really quick too. You just save 2 of these and hybridize it like that to make an sp hybridized orbital. And then what does that look like? Well, sp is linear, so I'm going to have my linear arrangement. The purple in the middle there, oops, is my linear. So here's my linear right there. And then this would be 1 pi bond, top and bottom. And then my other pi bond would be front and back. And that's allowed because, remember, unhybridized p orbitals are orthogonal. One's going to go along the x-axis, one's going to go along the y-axis, and the other's going to go along the z-axis. Well, if the x-axis is where my sigma bond is happening, the other options are where my pi bonds happen. This diagram just connects the balloons together, makes them one long balloon, instead of having that dashed line over them. I think it looks better, but it is a little bit more chaotic and confusing. And then finally, if you want to go to higher levels of hybridization to get sp3d and sp3d2, you can do that by combining d orbitals, but you have to have an n equals 3 or higher. So combining 5 orbitals gets you sp3d. That would be for trigonal bipyramidal. And likewise for doing sp3d2 to get octahedral, you would combine 6 total. And so there's some examples of what that looks like. All right, I'm going to go back and cover the things that I skipped really quickly. This is just the short version that you'll want to know. Molecules rotate around sigma bonds. And the reason for this is because since the overlap is head-to-head, if I spin this guy around, it's still overlapped. So the orbital overlap is what is important. Now, if I had a pi bond would require me to have one orbital like this, and then the other one parallel to it. But if I rotate the bond, then what's going to happen is that this will no longer be parallel. It'll then be like this. And those can't overlap anymore. So if I try and rotate a pi bond, the pi bond will break. So sigma bonds rotate, pi bonds don't. So on this slide over here, these two are the same thing. Whether the CLs are on the top or one is on the top and the bottom, doesn't matter because this can rotate freely. But this molecule over here, these are unique because this cannot rotate. So double bonds and triple bonds are fixed. They cannot rotate. So these two molecules are unique. And so we have different names for them. So this is where you might see the term cis and trans come up for molecules, which we'll talk about more in organic chemistry. All right, I'm happy to announce that that is it. That is all I have. So I'm going to skip past all of the molecular orbital theory, which there's a lot of stuff in here. I used to teach this. In fact, this is the lecture that I was hired to teach, was MO theory. They liked it so much, they're like, we want you to teach here. But we don't really cover it anymore. Oops, I forgot that there was a ding sound in there. Let me hit mute real quick so that doesn't... There we go. All right. So let me put the slide summary up for the first bit. So you can pause and look at that if you'd like. And then the second bit. And then we aren't going to do MO theory, so you can ignore MO theory. But at very long last, doing the last chapter in an hour, because there's really just not that much to it that I care about. Congratulations. Somehow, against all odds, we have survived Chemistry 161. That's it. That's all I got. The end. So I realize the end is a little bit rushed, but remember the main points that I care about from Chapter 5, which is just know what a sigma bond is, know what a pi bond is, assign the correct hybridization code to each geometry, and you're good. You will do fine in 261. And you'll learn it all again there, because we spend a lot of time on it then with actual model kits, and you get to build stuff, and it'll be fun that way. So, yeah, so that's the end of this class. I hope that everybody found it... Oops, I just clicked on something I didn't mean to. I hope that everybody found it enjoyable. I know it was really difficult at times, particularly Chapter 3. But I do want to thank everybody out there who's been watching the lectures, attending the lectures, participating in the chat. Whatever it is, the people that I recognize your names because I talk to you in Discord or in the chat all the time, or even to those people that I've never even met, don't know who you are, and I probably never will because of how the pandemic is going on. I just want to say thank you. Without you guys, this class wouldn't have been possible. Literally, they would have canceled it. So, thank you for that. I hope that you found the experience rewarding and that it helped you to understand chemistry at a deeper level than in 161. So, with that, I will just hit the last little musical bit, and I'll wish you a good rest of your quarter. Good luck on finals. I'll post an announcement about the schedule later. Have a good night.